friends, welcome to this lecture. So, in this lecture we will discuss a very important method, method of characteristics to solve a non-homogeneous problem, or we can say that Riemann-Green's method to solve a non-homogeneous problem. In this regard, if you recall, in the very first lecture of wave equation, we have solved one dimension wave equation, that is you can say that this problem, that is UTT equal to c square uxx. Here x is lying between minus infinity to infinity, t is greater than or equal to 0 with the initial condition, that is ux0 equal to f of x and utx0 equal to g of x. And here we have solved this problem by considering that since this is a hyperbolic equation. So, here we have say characteristic exists xi as xi of x minus ct, and here you can written as xi as x minus ct and eta as x plus ct. And with the help of this, we have reduced our problem, this problem, as u xi eta equal to 0, and then we saw after solving this we have obtained our solution, say u of xt is equal to 1 by 2 u f of x plus ct plus f of x minus ct plus 1 upon 2 c x minus ct to x plus ct g xi d xi. So, this so here we have used the method of characteristic to solve this one dimensional infinite string problem. Now, in this lecture we will again discuss the method of characteristic to solve the non-homogeneous one dimensional wave equation. So, let us concentrate on this now. So, here this method is popularly known as Riemann's method or Riemann-Green's method. We will see what is this. So, here consider the following linear second order hyperbolic equation, that is Lu equal to fxy, where Lu is defined as uxy plus axy ux plus bxy uy plus cxy u equal to f of xy, where a, b, c and f are continuously differentiable function. So, these a, b, c and f are continuously differentiable function with respect to the variable x and y, and since we assume this form as a canonical form, because if you remember that any hyperbolic equation, second order linear hyperbolic equation, can be reduced to this problem, this canonical form, that is uxy equal to Lu equal to f of xy. So, we are assuming that here x and y are your characteristics. So, here I am assuming that since this equation is already in its canonical form, so its characteristics are x equal to constant and y equal to constant. So, here your x and y are your characteristics coordinates. Okay. So, now we try to solve this Lu equal to f using Riemann's method. So, for that here let we assume Vx be another function having continuous second order partial derivative. Now, let us look at the following say identities. So, first thing is Vuxy minus Uvxy. This I can write as Vuxy minus Uvyx. If you look at how these two are equal, if you simplify this, it is what? Vyux plus Vuxy minus Ux Vy minus Uvyx, right. And if you cancel this Uy and Vy and Ux here, then what you will get? Vuxy minus Vxy, that is what we have written here. So, it means that this is identity we are using. Then I can write Avux equal to Avu of x minus Uavx, or you can say that here I am writing Auvx plus Uav of x equal to Avu of x. That you can simplify this, it is what? If you simplify this, it is what? It is Av and Ux plus Avxu. So, which is already written here. So, we are writing Avux as Avu of x minus u of partial derivative with respect to x of Av. Similarly, in the same way we can write B u v y as b v y u plus b v u y. So, here I can write b v u y as this minus this. So, b u v y minus u b v y. So, here we are using these identities. So, idea is that if we can write v l u minus u m v equal to u x plus v y, we just arrange it. Now, here what is m, what is v, let us see. Then I can write it m v as v x y minus a v x minus b v y plus c of v, and here u is equal to a u v minus u v y and v as b u v plus v u x, and here m is some operator defined in terms of v, and we say that this is an operator which is known as adjoint operator of L. So, here let us again see how it is done. So, here what we have done, here it is L u equal to f, and here L u is defined as following: u x y plus a u x plus b u y plus c u, right. Now, here we define your m of v as v x y minus a v of x minus b v of y plus c v. So, we now to find out v of L u minus u of m v. So, this we want to find out. So, what is this? Here we can write v u x y plus a v u x plus b v u y plus c u v minus u v x y plus v u a v of x plus u b v y minus c u v. So, this will be cancelled out. Now, this term v, so here v u x y minus u v x y, which we have approximated like this: v u x y. So, v u x y minus u v y x, u v y of x. So, this term minus this term we have approximated like this. Now, this how we write it here. So, this a v u x and here this thing, how we can write it here. Let me look at here. Okay. So, here we have written a v u x. So, here a v u x as a v u x minus u f a v x. So, let me write here say a v u x plus u a v of x. This we can write a u v of x, and that we can see it here, and then we can write b v u y plus u b v y, and this we can write it as b u v of y. So, it means that all this thing I can write it like this. This I can write it v u x y minus u v y x plus a u v x plus b u v y here. So, now let us collect the here a u v minus u v y derived with respect to x plus v u x plus b u v y. So, call this quantity as u and this quantity as v. So, look at here, what is your u? So, u is a u v minus u v y. So, a u v minus u v y, and v as b u v plus v u x, b u v plus v u x. So, we have written that how this if we take L u as this, m v as this, then you can write the v L u minus u m v as u x plus v y here. So, this is now your u x plus v y here. Now this is some identity which is known as Lagrange identity. It is similar to your ordinary differential equation. In ordinary differential equation we have written the similar kind of identity, and these two identities are known as Lagrange's identity, and the operator M which we have defined here is known as adjoint operator, and in a similar way as we have defined for ordinary differential equation, that if M is equal to L, then L is called as self adjoint operator. So here if you look at what is the difference between L and M, in L you have written as uxy plus aux plus buy plus cu. So here if you look at uxy is now vxy, and aux is now written minus of avx, and buy is minus of bv y derivative plus this term is non change. So it means that there is a sign change in first order derivatives and no other change. So here first, third, and this is only for second order. If it is higher order, then first, third and order terms will have this kind of change, and even order will not have any kind of change. So here we simply say that if M is equal to L, then the operator L is said to be self adjoint. Now we recall a very important theorem which is Green's theorem, and we will see that how this Green's theorem is very useful in solving our problem. So what is Green's theorem? So let C be a closed curve bounding the region of the integration D, and U and V be differentiable function in C and continuous on C. So let us say that C is what? C is the some kind of, you have a domain, and C is this, and D is the domain enclosed by this curve C, and U and V are differentiable function inside your domain here. So U and V are some function which is differentiable on this, and on boundary it is continuous. So how this double integration which is done inside your region is now thrown to the integration on the boundary. So here your area integration is now reduced to line integration. So this is the power of Green's theorem. So here you can write ux plus vy dx dy taken on the region D is now converted into line integral u dy minus v dx, and this is the orientation, that it is clockwise here. So then ux plus vy dx dy integration over the domain D is now line integral u dy minus v dx over the contour C, and this is a having the direction anti-clockwise. So it is like this. So now let us see how this Green's theorem is utilized to find out the solution of non-homogeneous wave equation. So here let us start with, let gamma be a smooth initial curve, and since characteristics are x equal to constant, y equal to constant, so we assume that the tangent to gamma is nowhere parallel to x or y axis. So we consider this is your x, this is y, and suppose your gamma is given like this, and so here it is your gamma. And now so here we are assuming the initial curve in a way such that if you take the say tangent at any point of gamma, tangent is nowhere parallel to your x axis and y axis. So now we want to find out the solution. We suppose that u, ux and uy, in fact u and normals of u are prescribed on gamma, and we want to find the solution in the neighborhood of this gamma. So let us say that we have a point P whose coordinates are alpha beta, and here we want to find out the solution of the non-homogeneous problem. So this initial problem is known as Cauchy problem. So here we want to find out the solution of this initial value problem. So let us say you find out the characteristic parallel to your axis. So here we say that this is P, and let us say this is Q and this is the R. So it means the characteristic drawn from P will say cut the initial curve in 2 points, that is P, Q and R. So now we want to find out the solution at this particular point. Okay. So let us say that D be the region bounded by the closed contour P, Q, R, P. So it is P, Q, R, P. So it is the contour. Now D is the region bounded by this. So here by applying Green's theorem to this region we get what? So here if you we already know that V Lu minus U mv dx dy by Lagrange identity we can write that VLU minus UMV is your this is what, this is nothing but your U dy minus VDX. Let me write it here, sorry, here this is what, this is double D and it is what, Ux plus Vy dx dy, right. So, this is where we have utilized the following thing. Here we have utilized this property that here VLU minus UMV equal to Ux plus Vy. So, here we have written Ux plus Vy. So, Ux plus Vy. Now, we apply Green's theorem and we can write this as integration U dy minus Vdx. So, here again let me write it here, this is your P, this is Q, this is R. So, Q R P. So, here we have D. So, then integration on the region D is now thrown away to its boundaries. So, it is integration C U dy minus Vdx. Now, this boundary can be truncated into this term, this is QR. So, U dy minus Vdx on QR and plus Rp. So, here it is U dy minus Vdx on Rp plus it is on PQ. Now, if you look at in this line Rp, your this is alpha beta. So, your x is fixed. So, x is fixed. So, x is here alpha and here it is y equal to beta. So, x is fixed, so it means that if you take the dx then it is 0. So, on Rp your dx component is gone. So, here we have only u dy. So, on Rp we have only term u dy and similarly on PQ your y is equal to beta. So, it means that dy is 0. So, dy equal to 0. So, we have only one term left, that is minus of PQ Vdx. So, here integration VLU minus UMV dx dy, which is given as integration double integration Ux plus Vy dx dy, then use Green's theorem, we write it line integral u dy minus Vdx and then we truncate. So, using the expression for C we have written as along QR plus Rp plus PQ. So, along QR we have this, along Rp dx component is missing because dx is 0 and along PQ we have only dx component because dy is 0. So, now this expression is now written as sum of 3 integration from Q to R u dy minus Vdx from plus R to P u dy minus P to Q Vdx. Now, since we know that the expression of u and ux or uy only along the initial curve, but in the last term of the above equation we have term ux along the characteristics x equal to alpha. Here if you look at here, in here we, what is the expression for v? V expression is given as this, v is buv plus vux. So, here buv plus vux. So, here this ux we want to know on these characteristics, which we do not know because we really do not know what is the value of u of x along this PQ. So, what we try to do, we just simplify this expression so that we need only say the function u and its normal only on the characteristics, means only on the initial curve, not on characteristics. So, here we simplify this P to Q V dx in a following way. So, let us say P to Q V dx equal to P to Q buv dx plus vux dx. Now, here we can write it here uv from P to Q, we try to do solving this problem that we integrate it, integration by part, so that this derivative is shifted on this v, because so far we do not know what is v, we have just taken v as some twice differentiable continuous function, that is all. So, let us say that shift our derivative on v. So, here we can write it this as vu first integration of second. So, v into integration of u over pq plus p to q and differentiation on v. So, vx u and this term is already there. So, buv. So, we can write this as integration p to q v dx as uv from q to p to q plus p to q u vv minus vx dx. So, here now your derivative is not on u, it is on x. So, using this relation 77, now look at again this 76. So, here it is uv from p equal to uvq. So, this I can write it here, this as uv at Q minus uv at P plus this term. So, now take that side. So, we have uv P equal to uv Q plus P to Q u bv minus v ax dx plus this P to R u au av minus vy. This we are writing this only this here we have not changed anything. So, what we try to do from this, you just take out the value here. So, we have P to Q v dx equal to this whole thing. So, here we have double minus Q to R u dy minus v dx minus R to P u dy. So, that is what we are writing here. So, then it is UVP equal to UVQ plus P to Q UBV minus Vx dx, that is the term which we have obtained from 77, and then P to R UAV minus Vy dy, we are just writing minus Q to R U dy minus V dx, that is on the initial curve plus double integration. Now, so far the function Vx be an arbitrary function having continuous second order partial derivative, we do not have any information on V. So, let us, if possible, now choose function Vxy alpha beta to be the solution of the adjoint equation mv equal to 0. Now, we are putting condition on m of v, so that our problem is reduced to a simpler problem by which we can find out the solution at a given point P. So, let us say that Vx equal to Bv on y equal to beta. So, on y equal to beta, so what we want? We want that this term should go on, this term will go. So, we want that Vy must be equal to Av along PR. Now, what is PR here? So, PR is this. So, along x equal to alpha, we want that Vy must be equal to Av, and similarly along PQ we want that your Bv must be equal to Vx. So, along y equal to beta, so y equal to beta we want that Vx equal to Bv, and x equal to alpha we want Vy equal to Av, and also that this Mv is 0. So, it means that V is a solution of adjoint equation. So, let us write it here, Vx equal to Bv on y equal to beta, Vy equal to Av on x equal to alpha, and V equal to 1 at x equal to alpha and y equal to beta. So, it means that at point P, at this point we want that V has to be 1, and if we do this, then our problem, now this solution is reduced to what, u at P equal to uv at Q, this term is gone, this term is gone, this term is also gone. What we have is very simpler value UVQ minus Q to R u dy minus V dx plus double integration VLU dx dy, right. So, now this will give you the solution of u at the point P. So, such a function will satisfy all these conditions, that it is a solution of adjoint equation and satisfy these initial values along the characteristics y equal to beta and x equal to alpha is your characteristic lines, and such a function Vx y alpha beta is called a Riemann function or Riemann's green function. And we already know that the Riemann function is a solution of a hyperbolic equation where the data is prescribed on both the characteristics passing through the point P alpha. So, this is one characteristic, this is another characteristic. So, your data is defined on the characteristics. So, we can say that here the solution, if data is prescribed along the characteristics, will give a unique solution. So, such a V is going to be a unique solution. Now, once we have this V, then our and the thing that L of u is equal to f, then we can write down our equation, last equation, in a following form, that u at P equal to uv at Q minus Q to R uv a dy minus P dx plus Q to R uvy dy plus vux dx plus double integration V f dx dy. So, f is known, f is known, V is known, and uv is known. So, and u and ux is known to you on the initial curve. So, you by 78 you can find out the solution u at point P using this formula, but here we have used only the condition u and ux on your initial data. Now, it may happen that on initial curve you know only u and ux, u and uy rather than u and ux. So, if you know u and uy only, then how we cannot use the equation 78 to find out the solution u at P. So, here we use one small identity, that is uvr minus uvq equal to q to r uvx dx plus uvy dy. In fact, it is what? It is simply along qr, it is d of uv. So, this we can write it uvr minus uvq. So, using this, if you simplify, here you find out the value of, here you can use the value of uvq from this. So, you can find out the value of uvq, put it back, and you can have this formula. I am not going to simplify this. You can simplify, you take out the value of uvq in terms of uvr and this integral, and when you put it back, it will give you the following thing: u at p equal to uvr minus q to r uvx dx plus vuy dy. This is unchanged. The only thing what we have changed here, this expression and this thing, this will be a change a bit, rest everything is same. So, u at p equal to uvr minus q to r uvx dx plus vuy dy minus q to r uva dy minus vdx plus double integration vf dx dy. So, this is the equation 79 will give you the solution of u at p when u and uy is prescribed on initial data, that is initial curve is this. So, here u and uy is used, right, but what happen if u, ux and uy are given along the initial curve. So, I cannot use 78, I cannot use 79 alone. So, what we do, we sum these 78 and 79 and have the following thing, that if both ux and uy are prescribed along the curve gamma, then we can find the solution by adding the previous two formula, and we have the following expression, that u at p equal to 1 by 2 uv at q plus uv at r minus q to r uva dy minus p dx minus half q to r uvx dx minus vy dy plus 1 by 2 q to r vux dx minus uy dy plus summation plus double integration vf dx dy. The solution at the point p alpha beta depend only on the Cauchy data along the arc qr. So, here we have utilized what? We have utilized only the value u and ux and uy on the initial data. So, by this equation number 80 you can find out the solution p if your initial data is u, ux, uy defined on the initial data. If only ux, u and uy is defined, then you can use equation number 79. If u and ux is given only, then you can use equation number 78. So, we have now 3 formula to give you the solution of your problem where the initial data is given along the initial curve. So, now let us consider one simple example based on this, so that we can understand what is what we have just explained. So, now the example is this: prove that for the equation Lu equal to uxy plus 1 by 4 u equal to 0, the Riemann's function, that is v, is j naught under root x minus alpha into x minus beta. Here j naught is the 0th order Bessel function of the first kind. So, here the problem is only to find out your Riemann's function, it is not the problem of solving the entire problem. So, here we have initial function homogeneous equation, and we want to find out the Riemann's green function. So, here if you have L equal to 0, then look at the adjoint problem, and since we do not have any say first order partial derivative. So, your the corresponding adjoint function is same, in fact it is a self adjoint problem. So, here m of v is equal to vxy plus 1 by 4 v equal to 0 here. Now, we have the initial condition along with this. So, here we do not have the first order derivative, means a is 0, b is 0. So, here we can say that vx equal to 0, which we have assumed in terms of a and b. So, vx equal to 0 on y equal to beta, and vy equal to 0 on x equal to alpha, and v equal to 1 at x equal to alpha and y equal to beta here. So, we simply assume that Vx is something into y minus beta, and this Vy is something into x minus alpha. So, let us here we try to see that, let us use that if V is a some function of say x minus alpha and y minus beta, then we can achieve this. So, let us say that let eta is x minus alpha into y minus beta, and let us assume that v is z eta. So, when we do this, then Vx is what? Vx is z eta y minus beta. So, it will be 0 at y equal to beta, Vy equal to z eta into x minus alpha. So, it will be 0 at x equal to alpha. So, let us say that using eta as x minus alpha and y minus beta, let us assume that V is some z eta. Now, we want to find out the z eta. So, to find out z eta, we have conditions. So, we can say that condition is what? That V at 1 at x equal to alpha and y equal to beta. So, it means that 0 is equal to 1, that is first condition we have, and what equation it will satisfy, that we have to find out. So, let us find out Vxy. So, Vxy is what? Z eta eta x minus alpha y minus beta plus z eta. So, that you can find out. So, here you differentiate with respect to y. So, Vxy equal to z eta eta, then y minus beta, and then if you differentiate again, you will get what? We differentiate z eta eta y minus beta, and you will get x minus alpha also, plus when you differentiate y minus beta with respect to y, it will give, you will have only z eta only. So, here z eta eta and then y minus beta into eta y. So, eta y is x minus alpha and plus z eta. So, Vxy is this. So, Vx equal to, so here Vxy plus 1 by 4 V equal to 0. So, this is the equation which we has to satisfy. So, here we have V xy is what? Z eta eta, this is what? This is nothing but eta we have assumed. So, eta z eta eta plus z eta plus 1 by 4 z equal to 0 and z 0 equal to 1. This is the initial condition which we know, that z eta, which is nothing but your green function. So, Riemann's green function must satisfy this ordinary differential equation along with the condition z 0 equal to 1. So, we want to show that this is nothing but j naught root eta. So, our claim is that this the solution of this problem is your j naught of root eta. So, how we can show? So, here we want to show that the solution is actually your z naught of root eta. So, for that let us show here that if we have x square, say z xx plus, let me use this notation, x square y double dash plus x y dash plus x square y equal to 0, and we already know the solution of this is your j naught x. Is it okay? So, solution is j naught x. Now, we want to show that what is j naught root x will satisfy, because we claim that the last problem, this problem has solution j naught of root of eta. So, we simply say that, let us say that you take x as root t and try to see that this will be converted into previous problem. So, here you can find out dx by dt as 1 by root t into 2, right. So, 1 by 2 into root t, and we can write it here dy by dx as what? Dy by dx equal to d by dt dy by dt into dt by dx. So, dt by dx is 2 root t. So, 2 root t dy by dt you will get. Similarly, you want to find out d2y by dx square. So, it is what? D by dx of dy by dx, and this is what? D by dt of dy by dx and dt by dx. So, this is what? D by dt of dy by dx is 2 root t dy by dt, and it is 2 root t. So, here if you differentiate this, you will get first thing, so 2, and it is root t, if you differentiate it is 2 root t dy by dt plus 2 root t d2y by dt square into 2 root t. So, when you can write it here d2y by dt square equal to, when you multiply here you will get 2 dy by dt plus 4 t d2y by dt square, that you will get, and so this is d2y by dx square, and dy by dx is what? Dy by dx is, we have already 2 root t dy by dt. So let us use this value, since x square is what? X square is t only. So t, it is 2 dy by dt plus 4 t d2y by dt square plus x is our root t, and dy by dt. So dy by dx, sorry, dy by dx is 2 root t dy by dt plus x square is again t, so y equal to 0. So if you simplify, what you will get? It is 4 t square d2y by dt square plus collect the coefficient of dy by dt, it is 2 t here, and if you look at here, it is again 2 t, so it is 4 t plus t y equal to 0. Now divide by 4 t. So if you divide by 4 t, it is d2y by dt square plus dy by dt plus 1 by 4 y equal to 0. So here when you divide by 4 t, we have the following equation: t d2y by dt square plus dy by dt plus 1 by 4 y equal to 0. And if you look at it is what? It is a transformation of the earlier equation whose solution is j naught x. So it means that here the solution will be j naught x, but here what is x? Here we have assumed that x is root t. So solution of this problem is j naught of root t. So solution of this equation t d2y by dt square plus dy by dt plus 1 by 4 y equal to 0 is your j naught of root t, and that is what we claim here, that the solution of eta z eta plus z eta plus 1 by 4 z equal to 0 is j naught of root eta, and it satisfies the initial condition, that is z of 0 equal to 1. So here we have we said that the z eta is coming out to be j naught of root of eta here, and what is z here? Z is a Riemann's green function for the problem here. So what we have proved here, the corresponding the equation LU equal to 0, where L is defined as uxy plus 1 by 4 u equal to 0, the corresponding Riemann green function is j naught of root of eta. Now what is eta here? J naught of root of x minus alpha into x minus beta. So here we have obtained the green function of this. So once we know the green function, and if the problem LU equal to f is given, you can solve the problem LU equal to f in terms of v here. So with this I stop our discussion, and next class we will discuss our some more problems based on your heat equation. So with this I end our lecture. Thank you very much for listening. Thank you.